All right, so there's a lot, so more application problems. There's a lot in that last application problem. The next couple of application problems are much simpler than the last example. All right, so this is just a simple, actually, it's one we talked about when we were just doing, we actually did this application without derivatives in 2.1. All right, so more and more Americans are buying organic products. All right, AFT is in billions of dollars spent on organic food T years after 2014. So 2014 would be year zero. Right, then we asked two questions. All right, so the first question is estimate the amount the Americans spent on organic food initially in 2014. So remember, 2014 is time zero. It's just asking you for the amount. So that one's just asking you to take zero and plug it in. So what students will do is they'll take the derivative in this case and plug in it, but that's not what part A is asking for. Part A is just literally asking for what's the value of my function at zero at the start time. Well, the value of the function at the start time is that number out front. And so in 2014, they spent about, since we probably did round, 35.8 billion, not million, billion on organic food. All right, that's part A. Simply plug in zero or understand that that number up front is at the zero. The second part is asking for the rate changing. All right, those are the keywords to say I want the derivative. How is the function changing? What is its rate of growth? What is its rate of decay? All right, so estimate the rate. Rate means speed, right? Velocity that the Americans spend on organic food is changing, and change indicating I'm looking for a rate of change in both 2014 and then again in 2017 and then compare. All right, so we want the rate, which means the derivative. In 2014, so times zero, and in 2017, which would be 3 years later. Derivative first. So the derivative of a of t, so this is going to require my chain rule. The first thing you do is write down the original function, 35.8e raised to the 0.104 times time, but I'm not done yet because there's that number times t. I've got to remember to multiply by that number, so 0.104, and then I clean it up, multiply my 35 times that number, so my derivative, when I clean this up, and leave it exact, don't round, excuse me. Alright, so the derivative is 3.7232e raised to the 0.104 times time, where time represents time since 2014. Alright, find it at time 0, right? That would be 2014. Well, that's that number out front. Alright, because that becomes 1, because I put a 0 in there. And so in 2014, the rate they spend on organic food is growing, because it's positive, by about, since I'm going to round, $3.7 million per year. All right, so 2014, people were increasing their spending as a total, all the American people as a total, were increasing their spending on organic food by $3.7 million per year. All right, now in 2017, which would be time 3. Now we plug 3 into that derivative. So again, now I'm going to plug 3 into time. So I'm going to be very careful with plugging in my numbers in. So 3.7232 times e raised to the 0.104 times 3 comes out to 5.0865 if I round a few decimal places. All right, so remember it's in $1 million. So in 2017, the rate they spend on organic food is growing. You can read that, growing by about 5.1, if I round to one decimal place again, million per year. And so both of the years, the rate at which people are spending money on organic food is increasing. It's increasing faster. So to compare, all right, so both years, the rates are increasing, but in 2017, the increase is bigger, or however you want to word it. It's a faster rate of growth, right? It's 3.7 million in 2014. It grew, so that's how fast it's growing by. In 2017, it's 5.1, which is a bigger growth. So they're spending faster, right? It's a faster rate of spending. So they're spending more, and they're spending at a faster rate in 2017. So again, however you want to word that, I'll leave the wording up to you. Right, the last one, which again, the book talks about this, so there's a video like this on MyLab, so if you've understood the video they talk about on MyLab, you can skip this. But I want to come at it from, again, there's two ways you can solve this. So this is an application of whenever a problem says things are growing by compounding, all right, by compounding, all right, which means they're following this exponential growth equation, right, where k in that exponential growth equation is the decimal percent of growth. P naught is the initial amount at time 0. P of t is the future amount at t years. Right? That's this equation. Whenever it says growing exponentially, that's what that equation is. And so a lot of times we want to know the initial amount. All right, so the simple example here, suppose that grandparents plan to invest money into an account following the birth of their grandkid. They plan to make an initial investment. P naught's the initial investment. They would like it to grow to $40,000 by the time this newest grandkid reaches their 20. So over 20 years, they want it to grow to $40,000. Interest is compounded continuously at 5%. How much do they need to invest? Now, all right, so we're looking for the present value. The investment rate was 0.053, right? 5.3%, written as a decimal. The future value was 40,000, and time is 20, right? The kid was born, they invested the money, and it sits in there for their 20 years. So we want to find P naught. Well, there's two ways. The book talks about, the MyLab talks about how you can rewrite the equation, or you could leave it the equation, and you can solve it either way. All right, since the book talks about that method, I'm going to actually solve it using the original equation. So my original equation is my future value equals my present value, e raised to my growth constant times time. And so I plug these numbers in. So my future, well, I want $40,000 in my future. I want to find the present value, e raised to the 0.5053. And time was 20. All right? And so I'll probably simplify that 0.53 times 20. So 20 times 0.053 comes out to 1.06. All right? And then all you have to do is we'll divide by that e term. And so the present value is 40,000 divided by e to the 1.06. And the way the book sets up the present value and solves for it is they just move that up and make it 40,000 e to the negative 0.06. But remember, those two things are identical. If you type both of those in your calculator, you get the same answer, right? 40,000 divided by e to the 1.06 is exactly the same as 40,000 times e to the negative 0.06. Both of them should give you a present value of $13,858, and I'll go to the penny, 23 cents. And so the grandparents have to invest a little under $14,000. And in 20 years, since it's growing continuously, which is a lot, it's fast, that $13,858 will grow to $40,000. All right, so their grandkid will have $40,000 to spend on college or whatever. All right, so that finishes up applications of the exponential function. The last thing from chapter 2 is the logarithm, which is the next section, and we'll get that in the next videos.